In this talk, we're going to discuss solutions and some of the general properties of solutions. So first, a few definitions. A solution is a homogeneous mixture. A solution contains a solute, which is the substance that is being dissolved, and it contains a solvent, generally the more abundant substance and the substance that is doing the dissolving. The homogeneous mixture, of course, means that the solute is evenly dispersed throughout the solvent. So you have a homogeneous mixture as opposed to a heterogeneous mixture. A lot of times water is used as the solvent. It's sometimes called the universal solvent. And so solutions that contain water as their solvent are also called aqueous solutions, sometimes abbreviated as AQ. Solutions can be made up of many different combinations of substances. You can have two gases mixed together, gases and liquids, two liquids, etc. So pretty much mixing any two things together where you get a homogeneous mixture would qualify as a solution. You can see some examples here. So when you make a solution, when you prepare a solution and you dissolve a solute in a given solvent, we say that that solute is soluble. Now, not everything is soluble. So you can mix oil and water, and of course the oil is not soluble in the water. It doesn't mix. So soluble is a term used to describe two things that or a solute that readily mixes or forms a solution with a given solvent. Now, solutes behave differently depending on their chemical composition. Some solutes dissociate when they are soluble. When they dissolve, they dissociate into their component ions. So solutes that dissociate completely are called strong electrolytes. And a couple of examples of those would be ionic compounds that are soluble in water. So here you can see we have sodium sulfate. And sodium sulfate is an ionic compound, contains a cation and an anion. And when sodium sulfate is mixed in water, dissolved in water, it's soluble and it dissociates to form sodium cations and sulfate anions. So it breaks apart into its ions, and these ions are solvated by the water. Strong acids are also considered strong electrolytes. Something like hydrochloric acid. Hydrochloric acid will dissociate to form a hydrogen cation and a chloride anion, and so it dissociates completely into its ions, so it is considered a strong electrolyte. Some solutes dissociate into ions, but they don't dissociate completely. Examples of these, a couple of examples of what we call weak electrolytes, or substances that dissociate or break into ions but not completely, would be hydrofluoric acid. Hydrofluoric acid dissociates to form a hydrogen ion and a fluoride cation, anion. But if you had 100 molecules of hydrofluoric acid, maybe only 2 of them would break apart or dissociate. The other 98 would remain in their associated form. So that would be considered a weak electrolyte. Acetic acid is also a weak electrolyte. It's a weak acid. And so again, if you had 100 molecules of acetic acid, maybe only 5 of them would dissociate or break apart in their ions, whereas the remaining 95 would remain in their associated or non-dissociated form. And we also have solutes that are soluble but do not dissociate at all into ions. And these are generally molecular compounds that are soluble in water. So an example of that would be something like glucose. If you take sugar, glucose, and you dissolve it in water, it does dissolve, but because it's a molecular compound, it doesn't contain ions, so it does not dissociate into ions. So it's important to dissociate that some molecular compounds are non-electrolytes. Those do dissolve in water, but they don't break into ions. Then you also have substances which are just not soluble, And if something's not soluble in water, then it doesn't form a solution. So it would not be considered a strong, weak, or non-electrolyte. Now, when we prepare a solution, we also have to consider the concentration. You can put a lot of solute into a given volume of solvent, or you could put a little. And so it's very important to appreciate that solutions must be expressed with a concentration. And there's different ways of expressing concentration. Many of us are familiar with molarity, which is moles of solute per liter of solution. But there's also several others that are readily used. A mole fraction is commonly used to express the concentrations of mixtures of gases, where you have the moles of one gas over the total moles of solution. Molality can be used to express concentration, where you have moles of solute over the mass of solvent in kilograms. And also our solution's concentration can be expressed as a mass percent, the mass of one component over the total mass of a solution times 100. A couple of other terms and definitions that we want to be familiar with solutions. We can have a saturated solution. A saturated solution is a solution that contains the maximum possible amount of dissolved solute. So say that you had sodium chloride, you put the sodium chloride in a liter of water and it dissolved. You can keep adding sodium chloride and it will continue to dissolve up to a certain point. That's the saturation point. If you continue to add sodium chloride past the saturation point, then the additional sodium chloride will not dissolve and will just sink to the bottom. It's also possible to have a supersaturated solution. A supersaturated solution is a solution that's been manipulated so that it is able to contain more than the equilibrium amount of solute. Generally, a supersaturated solution is prepared by taking a saturated solution, heating it up, adding some more solute so it's more readily soluble at a higher temp, and then slowly cooling it down. And that solute will sometimes stay in solution. And a few factors that affect the solubility of a solute in a given solvent is the temperature. Typically, if you increase the temperature of our solution, you're able to increase the solubility or get more ionic solid dissolved in a liquid. So temperature can affect the solubility. If you dissolve a gas in a liquid, generally gases are more soluble at lower temperatures. So ionic solids tend to be more soluble at higher temperatures in a liquid, whereas gases tend to be more soluble in a liquid at lower temperatures. And pressure can also affect the solubility, but pressure really only affects the solubility of a gas in a liquid. Pressure doesn't have any effect on the solubility of a solid in the liquid. So when you dissolve a gas like carbon dioxide in water to make a carbonated water, if you dissolve a gas in a liquid, if you increase the pressure, you're able to force more gas into the liquid, and so generally higher pressures increase the solubility of a gas in a liquid. And this can be expressed by Henry's law, which tells us that the solubility of a gas in a given liquid is equal to some constant K, which is specific to that particular solution, times the pressure. So if you can see that if the pressure is larger, if P gets bigger, then the solubility will increase. And finally, solutions have several physical properties that are different from the properties of a pure solvent. These are called colligative properties. It's important to appreciate that colligative properties depend only on the amount of the dissolved solute, but not its chemical identity. So if you had sodium chloride added to water and the same concentration of potassium chloride added to water, it would have the same effect on the colligative properties. So some colligative properties are boiling point elevation. So for example, if you had a liter of water. The boiling point of that pure water is 100 degrees at 1 atmosphere of pressure, 100 degrees Celsius. If you add a solute to that liter of water, the boiling point would increase. So that's a colligative property. The boiling point of the solution, the sodium chloride plus water, is higher than the solvent alone, the water by itself. If you took the water and a solution of, say, sodium chloride and water, and you measured their freezing point, the pure water would freeze at 0 Celsius at 1 atmosphere of pressure. The solution would freeze at a lower temperature. So the freezing point of solutions are less than that of the pure solvent. And also the vapor pressure of a solution is going to be less than the vapor pressure of the pure solvent by itself. And finally, solutions have osmotic pressure. So osmotic pressure is when a solvent moves from an area of higher concentration to an area of lower concentration. So all of these things are considered colligative properties, and so we'll discuss those a little bit more when we're talking about solutions.